Schrodinger himself was not trying to convince you that cats can be both dead and alive. He thought that was so idiotic that nobody could believe that, right?
Foundations of physics is the area of physics that deals with the foundational questions. How should we clearly think about our ontology? What is going on in quantum mechanics? How should we think about time? These are all questions that are in the domain of foundations. Now, it has a pretty curious history. It's not a formal department that you'll find in most universities. It's pretty much a collaborative space between physicists, philosophers, and mathematicians, all who are looking for formal, empirical, and conceptual clarity on what's going on in physics. It's really a field that had kind of been quiet for a long period of time until there's been a recent resurgence. Tim Maudlin is at the very forefront of that resurgence. He is the founder of the John Bell Institute for Foundations of Physics, and he is one of the foremost commentators on the works of John Bell. He is the author of many books on the metaphysics of physics, volumes on quantum mechanics and relativity, and a whole lot more. I highly recommend Tim Maudlin's work to anyone interested in getting clarity on how to even approach physics. This is my conversation with Tim Maudlin. What have you been working on? What have you been thinking about recently?
Well, I have a huge project I've been working on for years, which has morphed a little, changed in the last couple years, 3 years or so, to developing a new form of discrete geometry. So geometry with atomic elements that are not points. And that I hadn't really intended to be doing that. I was doing something else. I was doing the second volume of this, a volume that followed another volume I already did, and then I got caught up in this idea of really developing discrete geometry in a way that, to my knowledge, has not been done. So that's what I'm wrapped up in now, although I haven't had a lot of time to work on it recently.
So is that work on linear geometry mostly inspired because of your work on time?
I wouldn't say it's mostly. The first volume just arose because I was teaching a standard introductory course, as I've done many times before, and trying to present standard topology to the students, and realized I didn't really understand it. I mean, you know, definitions, and you can sort of technically follow them, but understanding how the definitions were expressing the intuitive concepts that they were named after, I realized it wasn't clear to me. And then thinking about it a bit more, I realized, and this is maybe one of the things that leads you to looking at discrete structures, is that the standard topological definitions don't really have any useful application in a discrete setting. So if you think that actual physical space-time might be discrete, and for all we know it is, and you know, there are various hand-wavy arguments that because of quantum theory it ought to be, then you think, gee, we don't really have the right conceptual tools. And then I thought a bit about how I actually thought about topology in the kind of standard way when people talk about rubber sheet geometry and these various transformations and what's invariant under the transformations. And I realized that you could just set the whole thing on a different conceptual basis. So that's what led to the first book. I can't say it was particularly about time, because when I started getting confused, it wasn't that I was dealing with time. I was just dealing with spatial structure and standard topological definitions. And then I did that, and then you realize when you do that, that time comes in a very in a particularly clear way. The difference, I should say, the difference between temporal structure and spatial structure, even in a unified space-time, can be introduced in a particularly clean and transparent way. And so then that tied up with some things about time, and that's happening also with this other stuff that I'm doing right now. That you know, there are 6 chapters of just doing spatial geometry, discrete spatial geometry, And then you say, all right, let's add time and do a discrete space-time, and then all this other stuff just falls out because of the difference between time and space.
Maybe it's just a good idea to introduce your ideas about time. What do you think the confusion around time in the mainstream of physics and more popular ways of thinking about it are?
Well, no, I think the popular ways of thinking about it are almost okay. I mean, I would make slight changes to the popular ways of thinking about it that come out of some relativistic considerations. But the error that I keep railing against is not in the popular conception at all. It's in a bunch of philosophers and a bunch of physicists who I think are confused. And that's just very simple, which is that time has a direction. Time is a directed kind of thing. It only goes one way, right? It goes from the past toward the future, and space just has no corresponding directionality to it, right? Space doesn't go from the east to
Right.
There's a formal technical property that a dynamics can have that goes under the name time reversal invariance. Then there's a very bad inference which says if the fundamental physics is time reversal invariant, then according to fundamental physics, there's no direction of time. And part of that is because the name time reversal invariance is also bad. It's just misleading. Here's an easy way to see it. So here's a feature that physics could have. It turns out not to have it as a matter of fact, but it could have, which is called parity invariance, or mirror reflection invariance. And if you want to say what that means, it's kind of intuitively you say, okay, somebody sets up an experiment in a lab and they get some result, some physical result comes out of the setup. And then you say, well, could you run that experiment, a kind of mirror image of that experiment? So, and you would understand what was meant. I mean, literally, if you're going to do it from ground up, where you're using right-handed screws, use left-handed screws, or, set up a mirror in your lab and you have this mirror image. Now build a lab on the other side of the mirror so that if you look through a window, it looks just like the mirror image, right? And then do the whole setup that way and then ask, okay, will the actual outcome of the experiment similarly be the mirror image of the outcome of the original experiment? Okay. If it is, then this thing has it has a certain symmetry called parity, spatial parity. Now, the thing to note is if you ask a physicist to do that, right, build me a parity reversed setup, they know what to do. But if you just go to a physicist who just ran an experiment and now you say, can you run that experiment reversing time, or can you run that experiment backwards in time or something like that? They're going to go, what in the world are you talking about? I mean, how am I supposed to do that, right? You can't reverse time. That's just not among the powers that you have. Now, there are things you can reverse. What you can reverse are time derivatives, like a velocity,
Right.
So you say, oh, look, here's something that's easy to do. In this experiment, I had a particle moving this way. Its velocity was this way. Okay, now do it, except the velocity is now spatially reversed.
Right.
But what you're reversing isn't time. I mean, time is still going forward, right? What you're reversing are time derivatives. So that can be done. But the fact, if it were a fact that the reversed experiment gave you the reversed outcome, that wouldn't at all tend to show that time doesn't have a direction. And on top of that, in fact, it doesn't always have the same outcome when you do that reversal. I mean, that's the violation of T, of what's called T symmetry, and that's connected with the violation of parity. So none of this stuff makes any sense, right? I mean, you introduce a formal definition, you give it the wrong name, and then even if I accepted everything you did, the actual physics breaks the symmetry that you're looking for, right?
Yeah.
So you say, what in the world are people thinking when they say time doesn't have a direction? Everything from your intuitive experience of your interior life to your intuitive experience of the world around you to the physics itself says time does have a direction. So I don't know, kill me. I don't understand it, right? I mean,
Yeah.
I think there are a bunch of bad arguments that have been deployed, and a lot of this is just going through and saying, notice this argument is bad, or this argument begs the question, or whatever.
Yeah.
But
I mean,
I kind of don't get it,
And it seems like the directedness of time is almost secure, independent of any investigation of what is more fundamental in physics.
I think the idea, of course, in any theory, there must be something fundamental in that theory. I mean, the theory is going to be based on some fundamental postulates from which you can then construct various things or abstract things or whatever. And there's always going to be a question, well, where do I stop, right? Where's a reasonable place to think maybe this is the bottom level and there just isn't anything below that, right? And of course, methodologically, that's an interesting question. But it turns out for time to be directed, it seems like a pretty natural stopping place. And it's also, as far as putting it into the mathematical representation, it's kind of trivial. In fact, we do it all the time. I mean, part of the problem is we do it all the time without thinking about it because there's this universal convention that when you have what you call a time coordinate or a t coordinate, that the direction in which, and that's a number, usually a real number, that the direction in which that number goes up is the forward direction of time.
Right.
Now that's clearly a convention, right? I mean, we could do it the other way around, right? You could, and when we launch rockets, 10, 9, 8, 7, 6, okay, we do down counting rather than up counting. The numbers get smaller. So that's just a convention, but the up counting convention is so universal that any physics student is just going to do that automatically without thinking about it, right? And maybe because you're not thinking about it, you lose track of the fact that there is this convention. I don't know. But the convention only makes sense because you think there's a direction of time such that you can state the convention, which is as time goes forward, make the numbers go up, right?
Yeah. I mean, I've never really understood what is achieved in thinking of time in the other way. In just being able to say that all time is everywhere at once, or that there's a block universe and that gets rid of any kind of time marker or directedness. What is the impulse? Because I can see conceptually how people might get there, but why do you think that kind of trend started in the first place?
Look, I'd have to go back, but we can lay some markers down, right? H.G. Wells writes this novel, The Time Machine. And if you've ever read it, in the introduction, there's this kind of lovely little lecture the guy gives. And he says, oh, well, there are 3 spatial dimensions and we can go up and down and left and right and forward and back. And gee, time is just another dimension. Why can't we go, forward and back in time? Now, the proper answer to that is because time just ain't like space, right? That's, and then this idea that time is just another dimension where the just means it's like just another spatial dimension. It's like a 4-dimensional, we're living as if you were living in a 4-dimensional spatial structure.
Right.
That gets reinforced a bit in relativity because people don't understand relativity and they said, oh, somehow space and time get all mixed up, and time, again, you'll often hear time just becomes another dimension, which isn't true at all in relativity because the metrical structure, if you do it, with a Lorentzian metric, distinguishes time-like directions from space-like directions, and it further distinguishes the time-like directions into 2 separate categories that don't connect with each other. So the future-directed ones and the past-directed ones. So that, again, the kind of directionality of time is manifest in relativity, in the fundamental geometrical structure. That time is different from space because all the spatial directions, you can go continuously from any one to any other. without leaving the set of spatial directions. So that is a connected set. And the temporal directions are not. They're just not. They're divided into these two classes. Okay, that seems natural to me. So I think there's a bunch of rhetoric, this rhetoric of a block universe. I mean, I had a long discussion once with a guy in another interview where he kept saying, well, do you or do you not believe in the block universe? And I said, well, I believe there is one past, and it's just as, the people in the past had just as much reality as I do now. And I think there's one future, and the people in the future who will exist in the future will be just as real as I am now. And so in a way, the totality of physical existence is a four-dimensional object.
Yeah.
If that's what it takes to believe in a block universe, I believe in one. But I also think part of that block is time, and I think time is directed.
Yeah.
And if you say, oh, then you don't believe in a block universe, then I don't believe in one. But I kept pushing the guy. The guy kept saying, no, the question is there this metaphysical presence that the future and the past have? And I said, I don't know what metaphysical presence is. You keep asking me these questions and you won't explain to me, right, what it is you're even asserting. And I can't kind of honestly tell you I agree or disagree, because I literally have no idea what metaphysical, what this magical metaphysical presence is.
It's an invented concept. Like, there's just the whole conceptual language of the block universe is so different from everything you learn in relativity.
Yeah, I mean, so part of relativity, I mean, the part of relativity that's kind of easy to explain, that does overthrow the intuitive understanding of time and the understanding of time that Newton used and everybody up until Einstein used, is the idea that the time structure produces this preferred foliation of universal instants of time that are global objects and that just succeed each other and foliate the thing, right?
Right.
And if you take special general relativity seriously, you say, no, it's not like that. And you have to get into the Lorentz metric, blah, blah, blah. But what does that have to do with whether the future is real or the past is real or whatever people talk about? I don't, is there this foliation? Now, my own view, now to come completely clean, is another thing I've been arguing for a long time, is that, I agree that Einstein had no reason to believe in such a foliation,
right?
But that's because all he was trying to recover was classical electromagnetism and gravity, and you don't need it. But once you get into quantum theory and violations of Bell's inequality, I think you do need it. Anyway, it's the easiest solution to formulating a clean theory that'll violate Bell's inequality, is to add a foliation back in. And that's a very controversial move, but again, it's kind of at least very simple. I can tell you what I'm doing, and I can tell you how it goes into the physics and how it shows up in the equations and blah, blah, blah. And it seems to me, just why not do the easy, people, oh, that's too cheap, right? As if, what's wrong with being inexpensive, right? I thought Occam was supposed to tell us, be as cheap as you can be, but
Start from the manifest image and then go upwards, rather than creating these metaphysical ideas and trying to squeeze them in. Okay. I mean, okay. So more broadly, I was trying to think of how to talk about the development of, how to talk about what physics is, how we should understand it metaphysically. But I think the best way to do it might just be to get your take on the history of 20th century physics.
So, yeah, I mean, I think it's useful when you go back and read Einstein, and anybody who hasn't read it should at least read his autobiographical essay in the Schultz volume, because it's very accessible and it's very nice. Einstein had very strong, clear physical intuitions about what he was doing, and also the way he thought physics was going. And he expressed them very clearly in some places. And one of those things in this famous letter to Born that he talks about was he looked back at physics starting from the ancient Greeks up to the late 19th century. and said, oh, it seems to be getting more and more local, right? Where both the ontology is local, that is, if you just take a little piece of space or a little piece of space-time, you can specify what's going on in there independently of everything else. And the totality is just the sum of all those little regions. And he said in the dynamics, because when you write down a field equation like Maxwellian electrodynamics, the dynamics itself is also local. So I can determine whether the fundamental physical laws are being adhered to, again, just looking in any little region of space-time and not having to look outside of it. And this was Einstein's thought that gee, things, the tendency of physics is more and more local. And then quantum mechanics comes along, right? Well, Einstein also kind of invented quantum mechanics on top of everything else, but once the Copenhagen, the Bohr kind of thing starts up, where there's measurement seems to have some special status and it collapses the wave function and so on. And the wave function is in some sense a complete description. Einstein's objection to that from the beginning, and this is again, just historically, people get this entirely wrong. They think what he was objecting to was the indeterminism, but it's absolutely clear from the historical record, he was objecting to the non-locality, right? He was objecting from day one to saying, wait a minute, you're telling me doing an experiment here can collapse the wave function, which creates a physical change instantaneously, arbitrarily far away. And that's absolutely contrary to relativity and everything he'd been thinking. So at that point, he kind of jumps ship, and Schrödinger also agreed with him and didn't think any of this Copenhagen stuff made sense. And then we know the history after that, which was that, Bohr was just better at organizing. I mean, he put together the Copenhagen school and he controlled a lot of resources, and he and Heisenberg and all these people, even if they had small disagreements among themselves, managed to form a pretty substantial block. And the dissenters like Einstein and Schrödinger didn't particularly much agree with each other, and they didn't operate collectively, right?
Yes.
They just went their own separate ways. And so this kind of Bohrian propaganda, took over. And then, as I like to say, I mean, early on, the Copenhagen thing was say a bunch of incomprehensible, weird philosophy and calculate. And then it came to the United States, and it was like, no, we need to make a bomb, right? Forget the first part, just shut up and calculate. And they, I don't think too many people will actually defend Bohr as having had deep insight, as opposed to this kind of weird, semi-mystical stuff he liked to say. And then you got to shut up and calculate. And of course, that's just, for a philosopher, or from my point of view, for a physicist, that's just a disaster. Calculating is boring, and doesn't give you insight. It doesn't answer the questions you're interested in.
Yeah, it's interesting. It seems like it coincided really well historically with around the time when philosophy and the sciences really began to split, not just from each other, but internally.
I mean, there's a split, but there's also a kind of weird, coincidental, unholy alliance between the logical empiricists who are, taking Hume's ideas, Hume's semantics, this kind of pure empiricist semantics, dressing it up in modern predicate calculus, right? And thinking, oh, they're either going to solve or debunk all traditional philosophical problems that way, right? Either here's the experiment to answer your question, or your question has no content. Right? So that's going on the philosophical side at exactly the same time this weird stuff is going on with Bohr on the other side. And then you can see all these kind of people operationists who are very sympathetic to saying, look, the only thing that really has any content is talk about middle-sized objects and all this talk about what's really going on at microscopic scale, or, you know, is the electron really smeared out, or is the electron really moving, and so on. Those are just empty. It's not that they're hard to answer. Because I can't reduce them to an experiment by this very naive empiricist semantics, they're literally empty. And you know, Carnap is writing stuff that's just literally Hume rewritten. So that there was actually this alliance between a particular strand of the early Vienna school, Vienna circle, and what was going on in physics at the time. Now, you know, the people trying to work out the philosophical side of it, like Hempel and so on later, and Carnap himself later, realized they couldn't do it, right? They realized the whole project falls apart and they couldn't complete it. But that news never got back to the physicists. And then at the same time, Popper's coming along with the same kind of deal, saying, look, you know, just if it's falsifiable, it's science, and if it's not, it's, you know, nonsense or whatever. And again, that was something that just gave them license to ignore these questions, fundamental questions that they should have been interested in.
It's a shame that logic is so disconnected from fundamental physics these days.
Well, you know, how much logic. So my, you know, what I always say is that mathematical physics has that name because you use mathematical objects to somehow represent physical reality. And the deep questions are about that representation relation, right? Well, how is this mathematical thing supposed to be representing physical reality? Which mathematical degrees of freedom are supposed to correspond to physical degrees of freedom? Which ones are just gauge? Is this supposed to represent an individual item or a collection, an ensemble, or, you know, a probabilistic? Is it a probabilistic thing? I think that's what's been ignored. How much literally logic, I mean, you know, Gödel's theorem or whatever, people somehow think Gödel's theorem is telling you something, which, you know, in physics, it's not. It's not telling you anything about physics. So I don't think pure logic has that much to do with it, but I do think thinking hard about mathematics, about mathematical structure and physical structure and the relation between them, that's where really interesting questions come up. But that's kind of why I've spent the last couple decades developing new mathematical tools, because I think, you know, this is, you need to ask yourself why you're using these mathematical tools as opposed to some others. And sometimes by some others, I mean, here's a brand new one, right? Try and use this, see what happens.
For sure. Like, I think that, like, lots of aspects of logic just don't apply. Like you mentioned Gödel incompleteness theorem. I think that's something that gets really popular for some reason, but I can't seem to find an application of it in physics, let alone anywhere outside of logic. I mean, I don't know how a problem in just a fundamental incompleteness in logic translates to incompleteness anywhere else. But I think I more meant that just the tradition of logic. Like, I think logic early on did involve these deep philosophical questions that, even if they're not directly related to things going on in physics today, they share intellectual heritage that kind of got split up and lost.
Yeah, I mean, there's also a bit of a danger on the other side. There is, as you know, this thing that people like to call quantum logic. And typically, it's just the theory of subspaces of Hilbert space under, you know, under intersection and span. So that's a perfectly good mathematical subject. But calling it logic misled them into thinking, I mean, it certainly misled Putnam quite directly and Quine quite directly into thinking that, oh, I'm going to solve physical problems by changing logic or by rejecting classical logic or something like that. And that's just silly. I mean, that didn't make no sense at all. You know, Putnam eventually worked out that it didn't make any sense, but he was sucked into it for a decade or so. So yeah, you also sometimes get this idea that some people want logic to do work it couldn't possibly do.
the way that you lay out how metaphysics should be approached, which, if I'm just taking a shot at it, is that you you need to consider the abstract formalism with the empirical content of when that abstract formalism ever engages with an empirical apparatus and interpretive framework. And I really do think you do need all three. And all these attempts that we're talking about right now seem to be examples of where you leave one of those out.
Yeah. And and as I've also said, I mean, it's common terminology now to talk about an interpretive framework, but I would rather just say a clear ontology, right? If you want to specify a physical theory for me, fine. Tell me what you think exists, right? And then tell me how you're going to use some mathematics to represent it, and those two things can go together. And how you're going to represent the laws or the way it behaves, the dynamics. But the part where you tell me what the actual ontology is, people call that an interpretation, and I don't. It seems to be a misleading word. It makes it sound more optional or more philosophical or something than it should be, right? I mean, as a physicist, you're asking, yeah, tell me what the physical postulates, and the funny thing is, the string theorists in the popular presentation of string theory were perfectly good at this, right? They would say, oh, here's the hypothesis. Ultimately, it's all strings. And gee, the difference between an electron and a quark is they're both strings and they're just vibrating differently, right? And you at least you understand, oh, that's what you're saying everything is made of, right? And these strings come together and they form these sheets and blah, blah, blah. Okay. To me, that's a story I can understand. Now there's going to be lots of details, and maybe when you get into the details, it doesn't work out quite the way you were expecting and so on. But at least you have a basic understanding what you're trying to do.
Yes, you have conceptual clarity, and then fields can go away because science is hard work. But at least you know what you're trying to do. Yeah. So, I mean, yeah. There is a lot of confusion with that folks don't understand the difference between a mathematical formalism and an interpretation or an ontology of it. Do you think that now just the foreground of that is quantum mechanics, or do you see that problem throughout physics?
Well, I mean, the biggest problems are, of course, in quantum mechanics as it exists now, because if you shive off space-time theory just to general relativity, okay, so you're kind of leaving behind, strong and weak nuclear forces and so on. But if you just kind of take a standard graduate level course in general relativity, and you understand the theory, which is okay, that's a big deal, but but it is comprehensible. I mean, I think general relativity, if you say, well, there's space-time, it has a certain geometrical structure, the rest of matter is somehow represented in this stress energy tensor. Okay, it gets a little vague at that point, or you think that looks a bit like leaving out too much detail. I mean, can I really pack it all into the stress energy tensor? But okay, and here's how the stress energy tensor interacts or plays a role in determining the geometry of space-time. And now let's look at all the kinds of space-times you could get out of this and how you would explain, various cosmological phenomena. I think that's all quite comprehensible and quite clear. Now, it may not be right, and it may be that's, at a certain level of description lying underneath that. And in order to unify that with quantum theory and with the actual detailed theory of matter, there'll be changes. But at least on that side, I think a good textbook, it's a really good textbook will explain that to you. If you go through Misner, Thorne, and Wheeler, or if you go through Wald carefully, you can get that. and those authors understood, I think, a lot of the detail, a lot of the mathematics, and they had the basic physical picture in their head correctly. But if you pick up any standard quantum mechanics textbook, there just isn't a clear physical picture there.
Right.
So yeah, most of the problem is arising on the quantum mechanical side. Absolutely.
Sean Carroll, for example, is famous for saying this, where they say that no matter what happens in quantum mechanics, it's unlikely that you're going to get rid of the classical world. It's unlikely that certain parts of thermodynamics and things will be, that they will stay the way that we know them to be now.
Yeah, I'm not sure. I mean, yeah, I'm not sure exactly what, I mean, Sean has this idea that he can make sense of the idea that somehow all of physics is, in the that we live in Hilbert space. The words that he would use, we live in Hilbert space,
right,
which is, it just sounds like, as we used to say, a category mistake. And that somehow space-time structure itself emerged. I know people talk about space-time emerging from entanglement and blah, blah, blah. That stuff I don't really understand. As far as classical physics, I mean, thermodynamics is, of course, a curious, everybody understands it has a curious standing.
Yes.
Because it's not, it doesn't postulate kind of anything directly physical. It's more consequences of statistical considerations that will occur in a huge variety of circumstances where you have large objects that are made of small objects with certain more or less mild constraints on how the small objects interact, that you'll get certain thermodynamic consequences out. And then you can understand why you say, well, that's probably pretty solid because it's so vague, because it's kind of abstracted at a level where it's going to fit even if you change the underlying stuff from particles to strings, for example. You'd say, well, gee, is that going to make any difference to thermodynamics? And your first shot out is say, no, I don't really see why. Yeah, I no longer have point particles. I now have these strings, but still there are lots and lots of them and they're interacting and,
I guess until there's ontological clarity at the quantum level, which seems like it's a little bit ways away, we won't know answers to questions like that.
And I don't know, again, I think that it depends. Again, it's a matter of definition. If you say by definition, what it is for a theory to be relativistic is to postulate that the totality of space-time structure is given by this Lorentz signature metric, then I actually think quantum relativity is wrong, because I think you need more than that. I think you need this foliation. So that's another case where, people might have said at a certain point, well, relativity is not going to go away. I guess I would say, I think something like a light cone structure, that's probably not going to go away, which is one of the insights of relativity, that in space-time itself, it has this light cone structure. You just have to be a little careful, and you should always be open-minded. I mean, people aren't open-minded enough. I mean, Bell famously said that usually what impossibility proves is a lack of imagination, right?
Yeah. So, okay, how did you become interested in Bell in the first place? It seems like John Bell left a huge impression.
Yeah, absolutely. I mean, I got interested. I can clearly remember and describe the day, which was the day when I picked up the 1979 issue of Scientific American with the dung beetle on the cover that had Bernard Despegnat's article on Bell's inequality. I'd never heard of it before then. And, I went back and looked at that article, and there are lots of things I object to now, but for all that, enough of what Bell did was clear that you could see this is really, really, really deep. This is really surprising. really shocking, really profound, seems to have direct empirical consequences. So you can really talk about checking whether this is, whether you're going to violate these things.
Right.
And it was just the most astonishing thing. I mean, I was reading the thing in my room, which was on the first floor. I was in college, and pacing. I was just walking, holding the thing and walking in circles, pacing. And I know that because I had friends who were outside and they saw me and they came in and they said, "What's wrong?" Right? Because they saw me like just with this magazine and this look on my face, right? Pacing and pacing and pacing. And that was it. I mean, as far as, I thought, look, you've got to come to terms with this. And it's not kind of vague and hand wavy and metaphorical or whatever. I mean, this is just solid. And even now you have to explain to people that it's not even about quantum mechanics. I mean, Bell doesn't mention quantum mechanics, and there's no quantum mechanical formalism that goes into the proof, right? I mean, this is just, you go into the lab, you switch your machines around and you record some data.
It is such a beautifully simple proof.
Yeah, it's just absolutely astonishing and not at all what you expect, right? I mean, certainly, again, the great regret I have, I mean, regret is the wrong word, but it's sad because it wasn't that much time difference between Bell's proof and Einstein's death. I like to believe that Einstein would have seen the point. And his, deep opposition to non-locality, confronted with this proof, and then if confronted with the data, he would have said, well, gee, I just got that wrong. I like to think that, right? But he never had the chance to see that.
Yeah, I mean, that would have been interesting.
Yeah. I mean, because people say that he was playing around with de Broglie-like things and rejecting them.
Yeah.
And, and he certainly was not fond of, he knew about de Broglie and he wasn't fond of it. And you think, yeah, because it's manifestly non-local, right? If your main objection to Copenhagen is that it's non-local, that the collapses are non-local, and you look at something like, de Broglie, you're going to say, well, that's just as non-local. It's kind of manifestly non-local. That's not helping me. I take it that was Einstein's view, but he never saw Bell's proof that you just can't get away from that.
Yeah, I mean, Einstein and Schrodinger, till the end, I think, were both very committed to keeping an open mind and trying to solve these problems. And like you mentioned, I mean, that's probably what stopped them from developing an opposition to Bohr, which, I mean, bittersweet, right?
Yeah. And I think, to me, it's so frustrating because when you go back into the history and you see that the non-locality was what Einstein put his finger on already in 1925. I mean, immediately it was like, this is what I don't like about the theory. And finally in 35, they get up to the EPR stuff, which is a really clean statement. And I'm sure, you've tried to read Bohr's response and you're going like, if physicists look at the EPR paper and Bohr's response and say, oh, Bohr won that debate, you're going like, okay, I give up, right?
Yeah. Yeah, I mean, the EPR paper, it's just so strong. Like, I think it is just such a strong hypothesis over show up and calculate. Like, I don't know, maybe I just haven't read enough of that history or Bohr's response, but yeah, I mean, I don't think there's anything to say about it until
and it's made even sharper. I mean, the nice thing when you look at the history is that because in the EPR paper they're just looking at position and momentum measurements, it wouldn't occur to anybody that there were any other measurements that you might be making, right? And then Bohm has this nice idea of just reformulating in terms of spin and looking at spin in orthogonal directions. But as soon as you do that, it immediately occurs to you, well, what if I, instead of doing it like this or doing it like this? What if I, continuously start to change these spin directions from each other? And then that gets you right to Bell, right? So there's you can kind of just go bing, 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 right? I mean, Einstein had this immediate right intuition that involved only a single particle, then kind of hypercharges it in the EPR paper where you're now looking at entangled pairs, but you really only have two observables that you ever think about. And then, Bohm takes that, puts it in the spin context. Now I've got an infinite number of observables that are continuous, continuous groups. And then that gets you to Bell. And, I mean, and as you know, we were that far from Bell's paper just disappearing without a trace. In the first volume of a brand new journal that went under.
What happened to Bell? I don't know what happened to Bell afterwards. Like,
well, what happened, what happened historically was that among the few people who read Bell's paper, and I think he may have even gotten a preprint of it or something, and I'm not quite sure why, was Abner Shimoni.
Really?
And, yeah, and Abner, he had this student, Clauser, right? John Clauser, who was an experimentalist. And then Abner said, oh, look, I mean, first of all, Abner understood the significance of what Bell did. And that, I'm sure, is in part because he was, a philosopher as well as, had a philosophical training as well as a physical training. So he could, see, oh, I see what's going, right? And he had this student who was looking for a PhD project. And you say, gee, I think we could actually do this experiment. But again, it was published in issue 1, volume 1 of a startup journal that didn't last more than a year or so, I think. And it could very well. And, Bell was not a big self-promoter. I mean, the guy was just, he's working at CERN, designing magnets and doing this stuff on the weekend. He's such a wonderful man. I mean, I met him several times.
Oh, yeah.
But, perfectly modest and just, just a clear thinker. I mean, there were just things that to him were so obvious that you have to fight with other people to get to see. But he certainly was not, he didn't seem to have any noticeable ego about this. I mean, he was just trying to get it straight, right? Just trying to get it right. And he would write these papers, and they're absolutely fantastic papers. He's a wonderful stylist, wonderful writer. But I don't ever have the sense that he was out beating his own drum or trying to draw attention to it, right? It's like, my job is to work this out and write it down clearly and publish it, and then, whatever happens, happens. I mean, that's the sense I got.
Yeah, it's interesting to see the similarity between Bell and Everett, where Everett left academia very, very early on as well, right? Where many worlds wasn't really... Was it that it wasn't taken seriously for a while, or was it just his ideas?
I've heard different things about that, and there are people who've worked on Everett biographies. So there was a kind of dramatic story, which as I understand it, is actually false. Okay, and the dramatic story was Everett worked out many worlds. His Wheeler was his dissertation director. Wheeler then arranges for Everett to meet Bohr and the Copenhagen people, which all of that is true. Mm-hmm. And Bohr says no, right, is not impressed by Everett. And, they have to kind of boulderize his thesis in order to get it. And then the kind of romantic story is that Wheeler became so disenchanted that he went off and did something else. I've read, however, that's just not true. It's like he never really had any intention to go into theoretical. He wanted to make a lot of money, which he did. And he
in the wrong place.
I mean, he was he had an odd personality and not a terribly attractive one. And I think he really did wasn't interested in being an academic. I think he was my impression is he was much happier, doing the kind of stuff he did. So I don't know that he was forced out or disillusioned out, as opposed to just, he kind of, as a graduate student, had this idea and was working with Wheeler. So of course, Wheeler would be very supportive of this large scale thing. And then, he just left and did something else. And then it was only later when Bryce DeWitt kind of revived it, that even you more get the sense that Everett himself kind of lost interest in it,
Right.
not for any other reason, but that he was just doing other stuff. And then DeWitt, starts to really advertise it, and then Everett gets brought back into it a bit.
Right.
But I also think Everett's theory is not what people now call many worlds. So
yeah, many worlds is
I think the situation is even stranger, because he's pushing this relative state stuff, and nobody talks about the relative state. And that's just not many worlds as it's now understood.
So okay, yeah. So what's happened from Everett all the way to what many worlds has become today?
Well, my understanding, and again, take this with a grain of salt, is it was DeWitt who kind of rebranded relative state as many worlds, and I think maybe even started using that very evocative way of talking about it, right? And of course, the attraction, anybody who worries about the foundational thing and thought, as I did when I was young, that the real issue was collapse, right? So when I was really young, the impression I got was that quantum mechanics had these damn collapses, and everybody kind of was indicating this Wigner, gosh, maybe the collapses are caused by consciousness. Wow, mind-body problem, bang, 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 And I remember being very, astonished by that and saying, gee, we're really seeing the effects of mind on the world. I actually had a very brief conversation with, I think, with Shimoni, as a matter of fact, about this when I was a young graduate student. But if you go that direction, you say, oh gosh, it's all in the collapses, and if the collapses are caused by consciousness, then wouldn't that be amazing? Which of course it would be. And I mean, I actually had the thought, you could build a machine that would tell whether something's conscious or not, because you can check whether it could manage to collapse the wave function. So if you're thinking that way, and then somebody comes along and says, well, Everett says there are no collapses.
Right.
And you go, well, I see how that would make a big difference. And then that leads you through this kind of, this argument to, then there are many worlds. And then you have something else weird to talk about. I mean, the first time I heard this, I've told this story many times, it's quite true. The first time I met Bell was at this NATO summer school in Arice, Italy, that was organized by Arthur Miller, like 62 Years of Uncertainty, I think it was called. Yep. And, there's a volume from it. And at that meeting, the talk that Bell gave was about GRW, and that was the first time I'd ever heard of GRW. And Bell, as he had been advertising the pilot wave theory, because he thought it wasn't appreciated, he was now advertising GRW. And I was sitting in the audience listening to this. And again, with this whole background of thinking, the collapses are, what triggers the collapse? What triggers the collapse? And then you sort of say, well, nothing triggers the collapse, just random. And I went up to Bell afterwards, after the talk, and I said, wait, you mean after all of this like drama, it just happens? It's just, it just happens. There's nothing more to say about it. And I said, you're satisfied with that? And Bell looked at me. I mean, he's just such a wonderful man, right? He's very calm, and he just looked at me and he said, you don't appreciate what they've done. And he was absolutely right. I mean, it was the correct response, right? And it took me a little while to work through why what they had done was so important. And he was absolutely on target with that, right? But it was a shock because, if you have this Wagnerian consciousness collapse in the back of your head and you read GRW and all that's just gone, right? There's no trigger, right? it's a purely random thing,
Yeah.
then you're kind of let down, right? And you have to get over your emotional deflation before you see, that they've actually created a precise, mathematically well-defined theory that you can analyze.
Right. Yeah. I mean, of all of the theories, I think of everything from quantum mechanics, it's the Schrodinger's cat and many worlds. That's the two most popular. Those are the ones that are most popularized these days.
Yeah, I mean, maybe you've seen, there's an interview in which I pointed out, which was rather a shock to the interviewer, that Schrodinger himself was not trying to convince you that cats can be both dead and alive.
Yes.
And he thought that was so idiotic that nobody could believe that, right?
Yeah, it was always supposed to be a reductio argument. He just hated the.
And she was shocked. You mean that when we're told about Schrodinger's cat, I said, yeah, that people are pushing it as if Schrodinger was trying to tell you this cat is neither dead or alive until you look. And he said, no, he said, that's so stupid. Nobody would believe that.
Okay, going back to GRW, but just in general, what do you think about trying to squeeze epistemology into foundational physics? Like the people who try to look for the connection between quantum mechanics and consciousness.
So, okay, you mentioned two different things. Let me separate them. One is epistemology and the other is consciousness. Okay, so and those are two quite different questions, right? At some point, I mean, epistemological considerations have to come in when you're asking yourself the question, how plausible is such and such a theory, right?
Yes,
but then
yes.
What's the evidence? What are the alternatives? How do I evaluate them? That's, baseline epistemological questions. Does consciousness come in? Well, I hope it doesn't, because I have no clue at all how to solve the mind-body problem, and therefore it seems to me, and it has seemed to many other people, that if you had to somehow get this all down to consciousness to connect to the physics, you're just never going to do it.
Yeah.
As I like to say, Newtonian gravitational theory will make perfectly good predictions about orbital lengths and when eclipses will occur. I mean, in conjunction with, say, geometrical optics, when eclipses will occur and so on. Newtonian gravitational theory makes zero predictions about anybody's conscious state, right? I mean, how could it? That there would be consciousness or what it would be. So physics from the beginning has never had to solve the mind-body problem to operate, or else it would have never operated. And it's not that puzzling how it works. It works by, on the one hand, making predictions about the motions of middle-sized objects. And then on the other hand, we think we know a lot about the motions of middle-sized objects by looking at them, even if I can't explain how my conscious experience is produced in that, right? Nonetheless, it is, and I take my conscious experience to be a pretty good indicator of what's going on around me. So that's how the methodology goes. I don't see any prospect at all of thinking that quantum mechanics will give you a better grip on consciousness than Newtonian mechanics. And one can say, I mean, in a very straightforward way, anything we thought we understood in terms of classical electromagnetics, well, really, the more accurate theory there is QED.
Right.
Quantum theory, right?
Right.
Of course, we want to say, of course, photosynthesis, involves quantum mechanics, because it involves photons. I mean, gee, that's not a surprise. It's not a shock, and it has nothing to do with consciousness, right?
Yes.
I mean,
as our technology gets more and more sophisticated, these things will come up. And
I mean, people might be saying, look, there are some features here that are explicable quantum mechanically that would not be explicable in terms of, say, Maxwellian electrodynamics. And that would be a point at which you might say, oh, now it's really a quantum explanation, that you're getting phenomena that only arise in the quantum mechanical setting and not at the level of, say, just classical electromagnetics.
Sure.
But sure, you would expect that. I mean, you would expect there to be some corrections. Now, whether I mean, people sometimes say things like, I don't know, birds orient themselves by some quantum mechanical
Yes.
superpositions,
Yes.
which I've never looked into them. Of course, there's the usual thought that a brain is too warm and too wet and
Yeah.
too decohered
Yes.
for there to be anything very, very, characteristically quantum mechanical going on.
Yes. And also just the baseline intuition that there's so much that was considered impossible to explain about the brain that already has been explained using the techniques of biology and cognition and stuff that's too warm and wet and big to have a quantum mechanical explanation. So I mean, why would we shift the enterprise around based on a hunch, based on just the idea that, well, this is complicated, consciousness is also complicated, this seems fundamental, consciousness also seems irreducibly fundamental, so they must have some intrinsic link between them.
Yeah, that's
You know what I mean?
that's wishful thinking.
That's
or
wishful.
Maybe anti-wishful thinking. I'm not sure, depending on how you think about it. But it's not a very good inference.
Yes, exactly. And I mean, I'm open to hearing people out about it, but I can't figure out how to start on it. It's just, yeah. What do you think about reductionism in general?
Well, as usual, you need to give me a definition of what you mean. Obviously, look, I mean, I have pretty detailed views about this. Let me at least sketch them out a little.
Okay.
One thing we want out of science is understanding, comprehension. And sometimes we get better understanding of a phenomenon describing it at a more abstract level than, say, the level of physics. Sometimes the understanding, exactly, you really understand certain things when you see how it's kind of independent of the details, the underlying details of the physics. So if by reductionism one means all the other sciences ultimately reduced to physics, I absolutely reject. I think different sciences and their conceptual vocabulary can give you insight that you don't get from even a complete physical description. Yeah. On the other hand, of course, the behavior of any macroscopic object is just the net result of the behavior of all its microscopic components, because I'm only waving my fingers around because I'm waving all the little parts of my fingers connected together around it. And of course, this behavior is susceptible of some physical analysis. To that extent, physics does have a more foundational ontological position to all the other sciences. I often like to say, look, in all the other sciences, you can always say there's always an out if your predictions go bad. And you say, in certain cases, that's not my department, right?
Yeah.
The doctor examines you and says, you're going to live another 20 years. You walk out of the doctor's office and get run over by a bus. Okay. And the doctor can say, look, that's not a failure of me, qua doctor, right? All I meant was that you were healthy, and it's not my job to predict bus accidents.
Right.
But the physicist never has an out, right? I mean, that anything that happens, they better have a physical way to have predicted that from within physics. Yeah. So all natural phenomena are physical phenomena, but they're not all biological phenomena. They're not all chemical phenomena. They're not all meteorological phenomena or geological phenomena. So there is an asymmetry there, right? And in a way, physics is more general and more fundamental in that sense. But as I say, you still get insight from the other sciences that you won't get from physics. And then there's another idea of reductionism, which is that it's always explaining the big in terms of the smaller. And then that goes to hell in physics itself, because quantum states are part of the fundamental explanatory apparatus, and they're not smaller, right? In fact, they're kind of global and holistic. So that's anti-reductionist under a certain understanding of reductionism.
Right. So, okay, that I'm clear on. And like I've been using the terminology of ontological versus explanatory reduction. Or I was talking with James Robert Brown the other day, and he used the idea of ontological versus methodological reduction. That although yes, everything is inherently physical, so there needs to be a physical state description, whatever state of analysis, whatever level of analysis that you're looking at physically, but you can't explain something political, for example, without using political vocabulary and political methods and levels of analysis at the level at which you're interested to do scientific understanding. So that I understand, that ontological versus method distinction. But help me understand the idea of emergence then. Like the way that scientists use the idea of emergence, not so much in fundamental physics, because I think that's where things totally go haywire, but beyond, sometimes seem to sneak a little something more ontologically in, that it's genuine emergence in the sense that there is some sort of ontological disconnectedness from the lower level of analysis, and I'm just trying to wrap my brain around that a little bit.
Yeah, and this is, again, the history of this is kind of confused. At some point, Brian McLaughlin did a lot of historical work on British emergentism. And you have the problem that people can use the term emergence in exactly diametrically opposed ways, right? So someone might say, look, individual molecules can't be liquid or warm or something like that.
Sure.
But when you put a bunch of them together, liquidity emerges or temperature emerges or something. Where there, it's just kind of statistical characteristics of groups and things like that. And the relation between the underlying and the emergent is very clear conceptually.
Right.
On the other hand, sometimes people use emergence to mean exactly the opposite, that you get some behavior at some higher level that was literally unpredictable, or you get something ontologically new
Right.
when you put things together. That can't be explained as just the collective effect of the smaller things. And so what they mean by emergence is exactly the opposite. Now, I don't believe in the second one. I mean, I think the analyzing things down into quarks and electrons or strings or whatever, yeah, that's, you're going to get that. If you get that right, then you get the macro image just by the collective behavior of those things, all explained by these microscopic laws.
Right.
Nothing new in that sense.
Right.
But the idea that the first idea, again, that there are conceptual ways of approaching things and explaining them that are not implicit in any physical description, and that give you insight. That's correct. And it goes back to, I mean, Socrates makes that point in Phaedo or Crito, when he's in jail and he's going to be murdered, right? When he's going to have to drink the hemlock, and he's complaining about Anaxagoras or something. And he says, they seem to want to explain everything by the matter, as if you understand why Socrates is sitting in jail by saying, I've got bones and they're sinews and they're bent in certain ways, and that's why Socrates is sitting in jail. But that's not the real explanation, right? The real explanation is because I think it's best to be here, otherwise I'd be in Boeotia or Megara at this point and having run away. And I think that's exactly right. And you're not going to get a description of intentional behavior by Socrates, what he was thinking, what he thought was best, the decisions he made. Those are not implicit in the physical description, and they float in a way a bit free of the physical description, right?
Sure.
Or maybe better, take Darwinian evolution.
Sure. Yeah.
Even if the world were made out of Democritean atoms, and we're entirely non-quantum mechanical, as long as the atoms could hook up and make larger things that had different properties, you would expect there to be evolution, right? So that entire conceptual scheme runs a bit, it only depends upon very generic characteristics of the larger objects.
Right.
And how those are brought about by the microphysics is kind of neither here nor there.
Right. And that just is the job of normal science, right? That even if you have a grand unified theory tomorrow, we will still have weak emergence everywhere. You won't be able to use that theory to explain the weather or language or any of these things. But I think when people invoke strong emergence, and I still have no idea what strong emergence is, it kind of just acts like a black box that you put something into, and you just say that, well, we don't have, not only do we not have an explanation, we don't even have the beginnings of what an explanation would look like. So we just call this thing strong emergent, and it's ontologically disconnected, and it must somehow come about in some extra.
I mean, as I say, the place where I see that is the mind-body problem, but
Yes,
that's the only
yeah.
place that I see it, right?
Yeah.
I certainly don't see that's the relation between physics and chemistry, or chemistry and
Yes, absolutely.
biology,
Absolutely.
or anything like that. Yeah.
Absolutely. Yes, those are reserved for, like, I think, mind. What do you think about people who approach the other, so math, numbers, ethics, aesthetics, things like that, those properties those topics of philosophical interest that have been around forever? What do you think about the same kind of thinking about those things?
Well, I think mathematical, I mean, I'm Platonist about mathematics. I think there are mathematical truths that are independent of physics, right? I don't care how physics turns out. It's not going to change the fact that 1 + 1 = 2, or
Right.
if Goldilocks conjecture turns out to be true, it turns out to be true, and changing physics isn't going to change that.
Right.
So yeah, I think these are just different sorts of real existences. Of course, there comes to be a problem if you somehow, and again, Plato talks about this in Theaetetus. He talks about these kind of very gross people who only believe in things they can hold in their hands, right?
Right.
And so if I say, gee, I believe in numbers, then a gross kind of person says, oh, you think that somewhere there's the number 2 and you can grab it.
Right.
It's in Plato's attic or something. No, it doesn't have that kind. It doesn't have a physical existence,
Right.
but it has an existence. I think that's certainly true for mathematics.
Yeah.
And I actually think it's also true for some parts of ethics. I think there are ethical truths, and they wouldn't come out differently if Newton had been right? Or, they don't depend on physics. Morality is a much more difficult case, right? Math is a cleaner case, and you think there are these kind of sharp-edged mathematical items that have mathematical relations among them that you discover. That's what mathematicians do. Ethics and morality is harder, and I don't have nearly anything like evolved precise views. But I do think that some ethical concepts like fairness, for example, I mean, fairness is a kind of property of symmetry when you say everybody's
Yes.
treated alike, And so just as there are mathematical facts about symmetry, there can just be a fact that such and such a practice that people with a certain color skin are treated entirely differently from people with a different color skin. That's just objectively unjust, right? That's just objectively unfair.
Right.
That's not just my opinion, or it's not something that even the collective belief of society that it's okay, that wouldn't make it okay, right? I think we make moral progress just as we make mathematical progress when we realize that certain practices were unjust and unfair, and hopefully we make them better. But the limits of moral truth are much more obscure to me, and I don't, I mean, look, I think in the case of morality and ethics and behavior, the obvious thing that interferes is self-interest. I mean, when ethics will stand in the way of your doing something that will be very strongly to your own benefit, people become very clever in finding ways around ethics. Often there are subject matters where you're not so directly involved, and so it's easier to be more objective, right, and not have prejudices that are pushing you towards certain conclusions. But in ethics and in everyday behavior, it's just the opposite, that you've got all kinds of self-interest that often being ethical will run against your narrowly defined self-interest. So it's more that than intelligence. I think quite honestly, I don't think do unto others as you would have them do unto you. Okay, that's not a principle that's complicated, like trying to understand, a Lorentzian metric or something. I mean, everybody understands what's being said.
Yeah.
Often they manage not to apply that particular principle, and then they come up with clever ways to try and get around it or ignore it or whatever, because if they were to apply it, well, gee, they shouldn't be doing so.
My interest in ethics has always been more political and economic, I'd say. Because, I mean, you're totally right about that. And I think most people have ethical intuitions all the time, right? Like if they're doing something that we would consider to be wrong, most people can discern that it is wrong. But, and those are interesting problems, and ethicists have a lot to say about them. But the real complexity for me enters in when you are doing something that's right, but you're participating in a system that is still propagating as something that.
Right. So from a practical point of view, they're always, you can't be a purist. You have to make certain compromises to live in the world, and where you draw the lines is not obvious. I mean, there's certain just facts that people tend to ignore a lot because it would get in their way. So one of the way people justify tremendous amounts of selfishness is this idea, well, I earned that, right? I did that myself, and so I deserve what I have. And I always like to say, look, if you think you deserve, in some moral sense, the life you live as a 21st century Western person, you're crazy. I mean, people in the Middle Ages worked a hell of a lot harder than you did. And they didn't get, are you going to say they deserved, right? That they didn't get what they deserved, or are you getting more than you deserve? I mean, the fact is that we live off the fruits of a human civilization that was built by millions of people over thousands of years. And none of us would have anything like the life we have if not for that collective effort. We are the inheritors of that collective effort.
Yeah.
And the idea that somehow, oh, but I got this money and the government is stealing it from me because blah 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 blah. No, step back and you'll realize you are embedded in a very large system and benefiting from it, and owe back to it in a certain sense, right? And all these other people on Earth who are in some sense equally the rightful inheritors of this. I mean, the idea that any private individual can control literally billions of dollars, it's kind of absurd. It's like, oh, he worked hard for it. No, I mean, figure out how hard a coal miner would have to work 24 hours a day to make the amount of money that Elon Musk has. No, yeah. Elon Musk didn't work that hard, right? I mean, he didn't get it by effort. It's not, compensating for the effort he put in. It's just a system that was built and is run by all these millions and millions of people, and certain people have managed to figure ways to siphon off unbelievable amounts of the collective wealth.
And I mean, what's even more annoying about that kind of commentary is when that's associated with true scientific innovation or breakthrough. Like, industry very rarely is at the forefront of true scientific breakthrough. It's more the academy. Like, that's where you see true scientific, and it's not a surprise as to why, right? Like, as an academic, the only obligation, the only constraint that you have on yourself is that you need to meaningfully contribute to your discipline. You need to add something to the conversation of understanding the world. But in industry, there's the constraints of creating something that has some applicatory value to it. And although you might create a really large enterprise and be super profitable, it's not clear whether that is progress in the same sense as scholarly progress is progress, right? One is genuinely pushing forward the enterprise of understanding the world. One is creating technology that is being, in order to make a judgment call on whether it is progressive or not, you would need to look at the distribution of it. You would need to actually do a thorough analysis of how it penetrates through society. And if you do a thorough analysis of how the big Western companies are penetrating through society, I don't think anyone can very conclusively say that it's ethical.
Obviously not, and it's not a shock, right? They're just greedy people, and there's a system that allows greedy people to satisfy their greed to kind of obscene amounts, and then they accumulate enough money that they can buy off the politicians who make the laws that allow them to do that, and you have regulatory capture and everything else. Yeah, it's really pretty crummy, right? I mean, look, there are certain aspects of technological progress that have been good but could be much better for humanity as a whole. But the credit for that certainly doesn't go to these small number of people who have profited obscene amounts off it, right? The credit for that, well, look, Tesla ended up completely impoverished, right? Westinghouse made a heck of a lot of money because he's not because he's a better scientist, because he's a better money maker.
Yes. The history of 20th century physics is a lot like that too. Yeah. I mean, I always wonder, like reading your work about the debate between Bohr and Einstein and the way that it all went down, I always wonder how much of it is related to the tight coupling between industry and academia, right? Like, is it that certain fields of physics have more departments across the world and all that stuff because they're so closely related to pushing out an innovation? And I'm not saying that in a totally negative tone, right? Like, there is huge upside to specializing. You are able to produce technology, you're able to produce productive forces at a capacity that's unseen in human history. But it's silly to not think that there isn't a theoretical trade-off.
Yeah, I don't know how much industry comes, and this is just, when I say I don't know, I literally mean I don't know. I mean, look, there's a kind of ideal. It's like in the founding documents of the United States, when you write all men are created equal, being written by a bunch of slaveholders. Okay, so there's a certain irony in that, but there was an expression of an ethical truth that then it took a long time and a war and so on to move us toward. So there's an idea that part of science is just inquiry into nature, irrespective of its payoff. And to some extent, that's true. I mean, look at CERN, right? I mean, the fact is, if CERN were to, I don't know, if it had found supersymmetric things and proved string theory, that would make no difference at all. Zero to manufacturing and industry, right? High energy physics at this point is not going to make any difference. It's just, it isn't. But there is still people enough have that ideal that, look, we're not just doing this to make money, right? We're doing this to figure out the way the world works. And similarly for certain parts of space exploration or sending up this James Webb telescope, it's not like, somebody's going to make a lot of money from the results of that. Now, there are always technological spin-offs, and we get Tang and we get, Teflon and this and that. But there is, there is a spark of actual idealistic pure scientific curiosity that's around. And people, some people just pay lip service, and some people do more than pay lip service. So I don't know of any point in the mess that became quantum mechanics where industry was involved, right? I'm just unaware of there being any episodes where I would say, gee, this was capitalism that was no, they managed to mess that up on their own, right? I mean, without help.
What do you think about, just because you brought it up, space travel?
I personally see no reason at all to send people into space. The idea of trying to get human beings on Mars just seems silly to me. I mean, what's the point? I mean, you're going to go one way and die there. I mean, some of this nonsense, this Elon Muskian nonsense, like we're going to save humanity by populating Mars. I mean, if we screw up the Earth so badly that it's easier to survive on Mars than on the Earth, then we deserve to be completely eliminated, right? We couldn't do, you could set off all the entire nuclear arsenal that exists and it wouldn't be as bad living on Earth as living on Mars. So this idea that people, I mean, sending up the Webb telescope, that's great. I mean, we're going to learn stuff. And, sending up robotic things that'll land on Mars and look around and dig stuff up. And, I think that's great. But this idea that manned space travel is something that is deserving of a lot of resources, I don't see it. I don't see any scientific.
Yeah. No, I don't know what's accomplished either. Yeah. Especially just like if you have the technology to make a place like Mars make humanity resistant to the climate harshness, why don't we use that technology on Earth?
Right.
We need it here.
Why don't we do much simpler things to avoid Earth getting as bad as it might get? I mean,
yes.
And for more people, a lot more people. Yeah. Yeah. What do you think of, sorry to delve into this popular direction for a little bit, but what do you think of the way science fiction is treated?
Well, science fiction is an interesting hybrid genre. Some of it relies on the science, a lot of it doesn't. But I don't even know that I want to complain about the stuff that doesn't. I mean, the example I use a lot is time travel. I mean, think about time travel in the movies. Most of the stories are logically incoherent. But they're not trying to be logically coherent. They're trying to illustrate counterfactuals, right? So what if such and such had been different? Okay, that's a good question. And one way to get at it is to say, oh, let's have a science fiction story where you go to the past and you alter it and then you come back. Well, of course, all of that makes no physical sense at all. But that's not what you're trying to do. You're just trying to illustrate the contingency of history or something like that. Science fiction, there are very few people who care about the science and want to get it right or try to work out logically coherent things. And of course, I appreciate that. You probably appreciate, all you zombies. Okay, that's a fun story. At least it makes logical sense, even if I don't think it's possible, right? I appreciate the craftsmanship that went into it. A lot of science fiction is just old-fashioned Western set in space. And,
right.
I mean, it's just used for, it's used for very different purposes. So I don't think one can say much about it.
Yeah, I mean, like,
a blanket.
Right. I think it's useful as a tool to get people initially excited, right? Like it's interesting to just get your imagination running. But I've never been one to be stuck in that moment of awe inspiration. Like if I see something that's interesting, it's beautiful, it moves you, it gets you interested in the physics or philosophy or whatever you're studying. But the next step is to go understand it. The next step is to do the hard work of trying to conceptually understand it.
And the other thing is, I mean, I don't know if I had this amazing experience, which I wish more people had and they could have, in Washington. I grew up in Washington, DC, and Observatory Circle is so called because there is, in fact, an observatory that was set up there back before light pollution made it an entirely pointless place to put an observatory. But this big telescope is still there, and if you go on appropriate nights, you can go up and you can look through the telescope. And I went once when Saturn was visible, and it was just astonishing. It was astonishing. Not, of course, I'd seen millions of pictures of Saturn, right? But what the emotional effect of realizing, wait, I'm just looking through a piece of glass. That thing actually exists.
Yes.
This isn't fiction, right? It's not imaginary. That thing, this amazing thing with these rings, and it's there, it's out there, it's over in that direction, right? I mean, I had the same kind of feeling the first time I went to Athens, and I was with an academic trip, and we were walking through the Agora And at one point, the guy brings us into a place and he says, well, we seem to be at the corner of this street and this street, and they're the ends of this building and blah, blah, blah. As far as we can tell, we are now standing in the room where Socrates died. Okay. And it just like, you know, your jaw drops open, and not because you knew he died, it happened somewhere, but it gives it this concrete reality, right? It lifts it above fiction.
Yes.
Like Socrates wasn't a fictional character. He really was a human being.
Yes.
And so I would think, you know, more of that to get people interested in science is, you know, that's the kind of thing Feynman was very good at, right? Of kind of just looking around him and saying, oh, you know, notice that funny thing that light is doing over there, or, you know, take your polarized sunglasses and check the light that's being bouncing off the sea there, and you'll notice this and that. And just like, it was him making these connections between the science and everyday life and things around you that really, you know, was inspiring. And I think that's more important than science fiction, exactly because you want that sense of concrete reality.
Yeah. Yeah, there's no philosophical or scientific supplement for experience. Like, I don't think science and philosophy can move you in the same way, nor should they, right? Like, if you're being constantly emotionally moved by your work probably has some problems in it. You should have more of a level head in thinking about these things. But I think that is, I agree, like what is a little bit discouraging about science fiction and how it's depicted a lot of times is that it doesn't stress the actual hard conceptual work needed to go from that moment of inspiration to that moment of understanding. And that requires you to challenge your ontology a lot, and it requires you to take a step back and say that I'm going to investigate this without any emotional attachment to this. I'm going to investigate this whether or not it turns out to be right or true or even coherent. And that's something that's often missing. Yeah. Yeah. Many worlds and time travel and all that, I think, are the key popular example of that, where it's just totally run away now.
Yeah, well, and both of those, I mean, as I say, often both of those are used as a prop for asking a different question, right?
Yes,
for asking
definitely.
questions about counterfactuals.
Yes.
Right. Which are good questions, but you don't need fake science, right? to illustrate them. But
Do you pay any attention to many worlds these days?
Well, I pay attention. I mean, I paid enough attention to it over many years to identify what I think are the, I mean, I would say at this point, in a way I didn't originally appreciate, they're just gaps. They're unsolved fundamental problems in the theory. Now, you never want to say they can't be solved, but I don't think anybody has any good ideas about how to solve it. And I think there are competing approaches that don't have these problems. And so I'm personally not motivated to try and work out many worlds to a point where I would think it comes up to a par with the others, because the others have things they need to have worked out too, right? I mean, you've got to go from non-relativistic to relativistic settings and this and that. I mean, all kinds of things to be done. The question is, where do you want to put your effort? And look, I just don't, I mean, my immediate intuition is that many worlds doesn't seem right to me, just as in a much milder way between a pilot wave and an objective collapse theory, the pilot wave approach strikes me as more likely to be correct, and the collapse theory seems more artificial to me. And so I'm going to put more effort in that direction, because it seems to me to be a more likely correct direction to go in. I don't, you know, just as pure physics, I don't quite understand why anybody would think many worlds is a good prospect. Now, you can't, I mean, scientific research ought to be spread out. It's like in evolution, you want a lot of variation, right? And you want some extreme variation way out in the ends, even if it's usually not going to work, because who knows, maybe, you know, maybe something very extreme will work.
Yeah.
So I don't want to say everybody should be following my research choices, but
Yeah,
I'm not particularly motivated to spend a lot more time on many worlds at this point.
I mean, the whole history of physics has been a lot of people coming out of the fringe, right? Like Einstein, I think you can generally say was way out of left field at the very beginning. But it does seem a little bit like things have settled down just because of how big the enterprise has gotten, right? Like we are just in a bigger world now with more people doing things. So more criticism is more thrown around easily these days. But I hear you. Like this is, you do crazy theorizing and maybe it works out.
Yeah, I mean, the other thing is you know, when you get deep enough into this, you got to get a little away. You realize that there's some really interesting ideas that are way under researched. I mean, I've just been talking to, and I'm setting up a workshop. I mean, helping him set up a workshop with Siddhant Das, who's been doing work on arrival time experiments,
Okay.
which they're, you know, technically fascinating, conceptually fascinating, and really within the realm of what people could actually literally go into their lab and do. And it seems to me that that to me, that's a really good use of time, is to, because it's something that just people haven't thought about enough.
Right.
I mean, so you know, here's a really simple question you can ask. So we know we've got the Aronoff-Bohm effect. Okay, so if we're doing these two slit experiments and we put a solenoid between the two slits, if this, you know, if depending on what the magnetic field in the solenoid is, the interference fringes will shift on the screen. So we know that that's all kind of worked out and even been checked and so on. Question: suppose I send particles through this apparatus and I change the magnetic field in flight, right? So at some point between when I release the particle and when it registers on the screen, I change that magnetic field. Question: at what point will there be noticeable differences in those fringes? Now, that's a damn good question. And it's not obvious what the answer is. And it's not only not obvious what the answer is, there are some considerations that suggest this might be a way to actually send superluminal information.
Mhm.
Now, it's a hard analysis, okay? And because arrival times, there's no time operator in the standard quantum formalism, it's not even clear how you would apply the usual techniques for making predictions. And you have to talk about how you implement the change when you suddenly change the magnetic field in the solenoid. I mean, there's all kinds of technical things here. And this stuff I think is just fascinating. And it's something that in principle, people can now, experimentalists are in a position where they might be able to do it. I mean, literally send particles one by one and change fields in flight and collect data. So, you know, there's so many different things to do, right? And you can do very fringy, very open-ended kind of explorations, but then there are other more concrete questions you can ask like that I think have been under-investigated. The one thing you want to avoid is, you know, there's been way too much canalization into a small number, and you saw it with string theory and high energy physics. Just way too much of the resources were spent trying to develop string theory at the expense of any number of other theoretical projects that people could have been working on.
Are you skeptical of string theory nowadays?
Oh yeah, I think everybody is. I think we know it's not right. I mean, why? Because CERN never showed up any of these supersymmetric. Didn't show up. Okay, I mean, even even Brian Greene is now saying you shouldn't call string theory because it's not really a theory. And people like Brian Greene are saying, well, we developed a lot of math and maybe it's good for something. Probably not good for what we were hoping it was going to be good for, which is coming up with a theory of everything. I mean, I think everybody understands that string theory is in deep trouble. And there were, of course, people warning from the beginning that it didn't have
Yes.
the kind of foundation that warranted that much consideration or that much effort. And you get these, oh, it's the only game in town. Well, geez, if you only give people jobs, if they're working on it, it's going to become the only game in town, because what else, you try to do something else and you get kicked out of the field.
Yeah. I mean, what do you think of, sorry, it's a random question, but what do you think about cubism?
I'm sorry. That's well.
Sorry, very left field question, I know.
If you want to tell me what cubism is,
I was hoping you could tell me.
No, look. There was a claim made in print by Merman and Schack and Fuchs that cubism allows you to have a theory that's local. So this now you're goring my ox, right? I've spent my entire life trying to exposit Bell's theorem and explain why you can't get out of the non-locality.
Yeah.
One thing sure is that the only sense in which they can try to make this a local theory is to make it, as they say, also a solipsistic theory, right? It's a theory according to which the only thing that exists is you and your experiences.
Yeah.
And the only point of physics is to somehow give you a good tool for predicting your experiences. And that's just stupid. I mean, what else can you say? No. Physics is supposed to be about a world that's out there independent of us. And we know a certain amount about it. We don't know everything about it, but we know a certain amount about it. One thing I know is that there are other people.
There is a world.
There is a world. Things happen in it. Things happen far away from me that I only find out about later. Okay. Experiments have outcomes that the outcome was at space-like separation for me. And I found out about it later because, I read, they reported it, stuff like that. I mean, there's nothing there.
Yeah.
There's just nothing there for the extreme view, but I don't know that there's anything there for anything. Again, if you want to tell me what it is, that in a way that it makes a more serious topic of conversation, I'm happy to have that conversation. I've read enough of it by the people pushing it to come to the conclusion that there's nothing there. It's just a distraction, and it's best ignored because you're not going to get anything out of it.
Is it in the same class of investigation as the "why is there something rather than nothing" question?
No.
Okay.
That's at least a clear question. Tell me what quantum Bayesianism is. Just tell me what it is. The application of Bayes' theorem? Well, you want to use Bayes' theorem? Fine. Nobody's got a problem with that. I mean, people have been using Bayes' theorem all along. There's some idea that they don't want to be realists about the quantum state, or they don't want to be, as people say, I don't like this terminology, realists about the wave function.
Yep.
Well, the quantum state, the wave function mathematically is what we use to make all these predictions. And the predictions are really accurate. And that seems to indicate that it's representing something in the real world. Now, that doesn't begin to answer all the questions you might have about it. But to say that it only exists in your head, which is exactly what people like Fuchs say. They say, you shouldn't attach a quantum state to a system, attach it to your brain.
Yeah.
No.
Yeah, like
how's that going to explain two-slit interference?
I think the most generous view of it is just that you're starting epistemologically, and they have a model of the brain as a fundamentally Bayesian system that is updating information as it comes in using Bayes' theorem. But I think I know.
That's ridiculous.
It's ridiculous not just physically, but it's ridiculous because it supposes
Psychologically, it's
solution to the
ridiculous.
mind-body
That's not what people do.
Yeah. Well, it also supposes a solution to the mind-body problem. Like, I think you have to take that as a fundamental starting point for what consciousness is to do the rest of it.
It's not clear they believe in minds. I mean, not a brain anyway. It's not clear they believe in brains. I don't know what they believe. I don't, you know, certainly if it were a psychological thesis about the way humans come to their conclusions, then it's just demonstrably false.
Yeah, but I mean, it's not even psychological. Psychology is a higher level of analysis. It's supposed to be an even more fundamental description of what mind is. So I mean, yeah, like it's psychologists don't have an opinion on it because they don't know what it is. Yeah, we don't have to. We can move on.
Yeah.
Yeah. So not a fan.
Yeah, I mean, you have to make, look, unfortunately, and I had to make practical decisions because I was writing these introductory books, and they were very, very restrictive in how long they could be. And there were certain ideas which I'm not fans of, but I can at least articulate what the idea is and what problems it's going to run into and so on. And with QBism, you can't even get that far, right? It's just a distraction. It doesn't solve anything. It's not well defined. If you try and say what it is, the things that come out of your mouth are so implausible that, you know, why am I wasting my time with it? There's serious people doing serious work. I don't think this is serious.
Yeah, that's what I mean. Like the part, I like the application of Bayes' theorem in cognitive neuroscience. That's something that's happening a lot and that's useful, but it's just creating local models that are predicting stuff, right? It's not making fundamental claims. So I was just curious if that has seriously made inroads into physics, but I guess not.
Well, I'm not even sure. Look, even in psychology, look, the reason why Bayes' theorem is so important is that it explains why certain absolutely almost universal errors are made by human beings in their reasoning, which they do. They make mistakes all the time. They make predictable mistakes. The kinds of mistakes that Kahneman and Tversky, for example, you know, detailed. If people were Bayesians, they wouldn't make those mistakes. They do. They're not Bayesians. You know, Bayesianism is an ideal. Is an ideal. It's not. It is not a hypothesis about actual human psychology, and that's why it's important, because you can use Bayesian analysis to explain why certain conclusions people are drawing, are using base race fallacies or whatever. They're drawing these conclusions that are bad conclusions. And the way you show they're bad is by showing that it's not what you get out of a Bayesian analysis. Right. But if someone then said, oh, but my hypothesis is that human beings are Bayesian, no, they're not. They're demonstrably not. They wouldn't be making all these mistakes.
Right. It would be psychologically unstable as a theory. Okay, fair. We can move on. I was just curious. I honestly don't know much about it, but it's like the new flashy thing on the block.
Oh, yeah.
Yeah. Okay, so what is the right way then to think about foundations of quantum mechanics? I'm careful to not ask you what quantum mechanics is, but what is the right recipe for people to do foundations work?
Start with the mathematical formalism that is used to make really good predictions. Okay, because I mean, first of all, the only reason to take quantum mechanics so seriously is that it does make really good predictions. You know, try and understand that. Now, it turns out when you try and understand what that formalism is, it's inherently vague. I mean, we know that because, for example, von Neumann, when he tried to give you strict mathematical axioms, he had to have both Schrodinger's equation and a collapse axiom, and he never told you, except with the words when a measurement occurs, right? He never told you when to use one and when to use the other, and these were explicitly different processes. Okay, so then you notice that, wait, that's no good. Yeah. So, I mean, this was the kind of thing that Bell often said. He said his problem with quantum mechanics as it was taught was that it was not up to the standards of clarity and precision that mathematical physics as such should demand of itself. And that's why he told me I didn't appreciate what GRW did, because they wrote down a mathematically precise theory. You know, it's true they did it in terms of stochastic processes, blah, 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 but it's there, as Bell would say, their theory was in the equations and not in surrounding talk, by which he meant saying, oh, when a measurement occurs, blah, 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 right? So the first thing is to try to demand that level of mathematical and conceptual clarity in what a theory is. Once you get that far, then you start to see, okay, there are different ways you can go. And you can go a kind of pilot wavy way. You can go a kind of objective collapse way. You can then immediately see that, at least in principle, those two approaches will make at least slightly different predictions in certain circumstances. Then you can start asking, well, what are those circumstances and how far can we check and what experiments have been done, right? And that's a very important thing. And, you know, Catalina Curcineo is doing experiments in Gran Sasso. There have been experimental constraints put on GRW collapses. How strong are those constraints? That's work that Roddy Tomolka has done. All right, those are clean questions. Many worlds is a bit different because it's committed to there both being no collapses and nothing except what's represented in the wave function. So the wave function is complete. And to my mind, it's not clear how that theory really makes connection with experimental data, right? The other ones, I kind of know how they do. I can explain how they do. And in that theory, I don't quite know what I'm doing. So there, I'm not saying it's impossible. And of course, there were, in addition, issues about how to understand probability in that theory that everybody noticed. And there's stuff about self-locating probabilities. And, you know, I mean, okay, though, first define what the issues are, then see if you can make progress on them. Be very clear, try to be as clear as you can about what the theory you're investigating asserts.
Right.
You know, what does it actually say there is in the world? And what does it say about how that behaves? And how do I connect those assertions up with experimental data? That's what you should be doing. And then if somebody comes along with a new theory, you have these baseline theories that are there in terms of their clarity and what maybe conceptual issues there are. And at least you can, you know, compare this newcomer to those. Maybe it's better, maybe it's worse. Maybe it's so far worse that you think, I'm not going to, you know, I've got better things to do than take this very unpromising looking kind of proto thing. Somebody else wants to work on it, fine, but you know, I'm not going to spend my time doing that.
Yeah.
But the main thing is just to demand clarity, right? Demand conceptual clarity and ontological clarity about what you're talking about. And you won't get that by just studying the physics books, because it's not in the physics books. I mean, that's where you've got to do some work to supplement what's in a standard physics book with the additional principles and explications that are needed to get you up to that level of clarity.
Yeah, very true. The standard physics books don't give you that ontology. You have to look beyond.
I mean, the phrase "shut up and calculate" would never have been formulated and so widely appreciated if physics hadn't gotten into a situation where they kept having to tell their own students, shut up and calculate, which meant the students had some questions, and instead of those questions being answered, they were just told not to ask them. And you know, that's just that's shocking, right?
Do you see it as do you see it as getting better?
Well, it's certainly better than it was 30 years ago. I think part of what happened historically, and this is a guess, is that shut up and calculate could live up until more or less the completion of the standard model, because the physicists who said it could at least point to, look, we made atomic bombs,
Right.
or we're making
Right.
chips, or, think of all the stuff you get out of the Standard Model. So they could say, look, maybe you don't like, and then, there were some honest physicists like Dirac who understood the foundational questions, but also didn't have anything to say about them, and he at least acknowledged them. And then there were the ones that didn't even want to acknowledge them. But at least they had this technological progress and experimental progress and predictive progress that they could point to. But since the completion of the Standard Model, nope. And it all, again, it kind of, most of it went into string theory, which seems to have fallen apart. And I think at the moment, many physicists are a bit at a loss about what to do. And so they're more open to philosophers, or I don't even like to say philosophers, right? People working in foundations who've been worried about these foundational issues that they were told not to worry about. I think right now physicists are more open to listen because they realize they're not quite sure where to go. Something went wrong somewhere. And maybe we should listen to some of the people who've been complaining that there's stuff wrong for decades. Maybe they were onto something. So yeah, I think there's a bit less arrogance because of the failure to find supersymmetry and so on.
Right. And like, I don't know what your thoughts are on the sort of definition of what philosophy is, but a large part of it, I think, is just some sets of questions that have just been the curiosity of philosophers forever, and they'll remain that until there are good models provided.
Look, as I like to say, go to the physics department, go to the biology department, go to the sociology department, go to the anthropology department, go to the English department. They all have doctors of philosophy, right? They all PhDs. All these questions were originally part of philosophy because philosophy was just a general desire to understand things. And at certain points, some subdisciplines became so good at answering certain questions that they set up shop. Newton was doing natural philosophy. That's what he was doing. Physics is, from that point of view, physics is philosophy. What's left in the philosophy departments are this kind of odd ragtag set of things that don't have all that much to do with each other, like ethics and certain parts of logic and so on, just because they're the things, they're the miscellanea that didn't spin off into their own departments. But the animating question of philosophy, as Plato would say, is what is it? TSD. What is that thing? What is it applied to anything you like, right? What is water? What is justice? What is virtue, right? What is knowledge? And that's just the fundamental question of curiosity. Everybody should have that. And the main things that philosophers have nowadays is because typically we can't answer our questions empirically through experiment, and we have to investigate them conceptually and logically, is you're trained to be very sensitive to ambiguities in expression, to fallacies in reasoning, and so on, because that's all we have to go on, right? We have to depend on clear argumentation. So we become sensitized to certain errors or certain ambiguities or vaguenesses and to the logical structure. And where you can't be corrected by experience, you really need to be pretty fastidious about that because it's all you got.
Yeah, I mean, those always seem like the more interesting areas of scientific investigation as well. The big theoretical questions are, to me at least, have always been the interesting stuff. The stuff that can be shut up and calculated about doesn't seem a whole lot of fun to spend time on.
But this is, I mean, when I got my degree in history and philosophy of science, and because I was specializing in physics, I had to take 3 graduate level courses in physics. And as I often say, in one of them especially, it's absolutely true. Insofar as the guy said anything of real interest to me, he said it on day 1. And that was setting up, what is the basic ontology? What are we doing, right? And then after that, it's like, how do I solve this equation using Green's functions? Okay, that's hard. But quite honestly, I didn't get any insight insofar as I ever learned how to use a Green's function to solve it. I didn't get any deep insight into the questions I was interested in from that.
Right.
Now, if you're building a bridge or you're designing a circuit and you need numbers, you need to do that, okay? If you're an engineer, I understand you need to do that. I don't want to denigrate the ability to solve equations, but there's a certain aspect, as I like to say, you say, you want to understand Newtonian gravity, it's F equals ma and F gravity equals gm1 m2 over r squared. It's like those two equations. Now, can I solve a three-body problem if I just stare at those equations? No, it's damn hard, right? But in a certain conceptual way, I want to understand those two equations to understand what Newton was doing. And then the numbers come out how they come out, right? And it's not that clear that you get deeper insight into tracing out exactly how those equations get solved in this and that circumstance.
There's a lot of, just to shift gears a little bit, but there's a lot of going to physics, cosmology particularly, and looking for meaning, looking for answers to these higher level philosophical problems, or at least what I would call higher level philosophical problems, just as a way of categorizing them. What do you think of that?
I think you're going to be disappointed. Well, I mean, we know enough about cosmology, just, we've known it since we had telescopes, to know that this universe we're living in is not the kind of universe an intelligent creature would make who had humanity at the center of their concerns. Okay, it just is. We're on this kind of random looking planet way out in the edge of this one galaxy, and there are all these other galaxies and blah, blah, blah. Okay, so that was a shock to people, and a blow to their amour propre to think that the entire universe didn't exist for the sake of humanity. But further advances in cosmology haven't changed that situation.
Right.
So yeah, I guess Weinberg famously said, the more he understands the universe, the more pointless it seems. And I think that's what he was expressing, right? Yeah. Cosmology is very interesting because they're interesting physical phenomena. And of course, we're interested going back in time and trying to figure out what happened 13.7 billion years ago and whether it goes back further and how it might go back further. Those are good physical questions, but I can't see that answering them give me any meaning or significance or anything like that.
Yeah, I mean, and that's not to say that you can't explore meaning. You just can't explore it in cosmology.
Yeah, I don't know why cosmology would have anything to say about it.
Yeah.
I mean, is the number of binary black holes in the universe something that's going to give me insight into meaning? No, not really. I mean, you kind of have to know what that is, and maybe gravitational wave astronomy will give us a handle on that. But the idea that, I mean, again, Socrates already said in Republic at some point, he's having this discussion with Glaucon about the different sciences that you ought to learn as preparation to do philosophy. And one of them is astronomy. And Glaucon says, oh, I see, because that makes you look up. And Socrates, no, you idiot, right? It's not that you're looking, that's not the point, right? And in fact, you're not supposed to pay too much attention to what the actual stars are doing, because you're supposed to be focusing on the mathematics and some,
yeah.
So yeah, I mean, cosmology is interesting. Microscopic structure is interesting. I mean,
Right.
So we're on just to clarify it, in cosmology, where do you think the confusion is coming from? Is it fine tuning?
Well, I think there is a fine-tuning problem. I think people who say, relative to our present understanding, the section of parameter space, when we look at what we regard as fundamental constants of nature of which we have no further explanation, and we ask, okay, we have a certain rather large number of these, and that by any reasonable way of talking about large and small, that the part of parameter space that would allow for complex structure, rather than just say a gas, okay? You know, I mean, imagine, look at all the complex solids we have, you know, just look around you, you know, paper and metals and, you know, things that can be put together and structured. Okay, so if all there were a neutron gas, you wouldn't have stuff like that. So you say in parameter space, there are these arguments, and as far as I can tell, I'm not an expert, but when I read the books, they seem pretty convincing, that in this kind of parameter space, the part of parameter space that allows for complex structure is really, 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 really tiny. And it seems to me, yeah, that's a problem. I mean, I would hate to have to say at the end of the day, it just turned out that way. Now, to me, there are two possible solutions to this. One is to get a deeper theory in which what seem to us to be independent parameters are actually consequences of single things that are deeper, and you really can't think of varying them independently of each other, right? Because they're deeply connected in some way we don't yet understand, and in exactly the right way so that they're going to come out in this kind of sweet spot. Or you have a kind of multiverse thing where there's some mechanism by which random sampling was made in this parameter space, enough random sampling that it becomes probabilistically quite likely that at least somewhere you'd hit in the sweet spot.
Right.
And then the weak anthropic principle just tells you, well, we'll find ourselves in the sweet spot because that's the only place where conscious beings like we are could evolve. That seems to me a perfectly good explanation, but that requires the physics of how does this variation occur, right? And I mean, that's the sort of thing that, you know, inflationary cosmology was, these bubbles and so on. I mean, they were trying to fill that in, and I appreciate that project. I would be much happier if a project like that could be carried out, because I think it would eliminate puzzlement about fine tuning. And if it can't be carried out, then I think that I am a bit puzzled that the parameters seem to fall in this very tiny little region where they would have to fall in order to get anything complex. So you know, there's some people who want to deny there's a problem. I think there is a problem. I think there is a problem. I think there are sketches of what solutions might look like. And there is a certain kind of multiverse solution that I think really is conceptually a solution, but then you need the physics to back it up, which we don't have yet.
Right. Yeah, I mean, like, I think it's a lot of work to get from mathematical formalism to conceptual clarity, and it might be even more work to get from conceptual clarity to meaning, like to exporting it in ordinary language where it could mean something to people.
The issue of meaning as it comes up in everyday life, I kind of, when my daughter was young, and we'd go out to the playground, and if she'd fall and, you know, and skin her knee, and you rush over and try and comfort her and make her feel better. Now, somebody can say, oh, but in the large scale of, you know, the cosmology, there's this, you're this tiny speck, and you know, yeah. Or this is just a bunch of atoms that are running around. You say, there's a child who's hurt here, right? And I want to make her feel better. And that has meaning in the sense that that's a meaningful thing to do, right? That's a good thing to do. I'm making the world better by this act. Yeah. Physics isn't going to tell me I'm not making the world better, and the size of the universe isn't going to make it any less significant. I mean, I think people, in terms of everyday, having meaning in their everyday life, if they feel like what they're doing is insignificant, then gee, find a job or a pastime or volunteer. I mean, there are lots of ways to make the world better. that are meaningful, and physics isn't going to, isn't going to destroy that, right? And cosmology isn't going to destroy that.
Yeah, and I mean, I don't even know if meaning of life is a coherent question. I think meaning in life is probably a very coherent question. I think that's an important thing for psychologists, cognitive scientists to come up with. Very important, but it's not going to have anything to do with cosmology.
Right, and meaning of life, suggesting that life exists for some purpose.
Yes.
Again, no, it doesn't. Look, all those dinosaurs lived for just millions and millions of years.
Yes.
What was their point?
Yes.
Then they were wiped out by an asteroid. What was the point of all that? Well, wasn't really a point to it. That's just what evolution threw up, right?
Yes. Yeah, I mean, like, theologians and people who think about this, like, I have come around in the past couple of years to at least listening to what theologians have to say, but kind of as an artifact of human, like as an artifact of understanding human experience that might be useful for psychologists or literaries to make sense of things, but you can't take the ontological cosmological claims seriously. You can take them analogously, but you can't take them literally.
Well, but it's deeper than that. And again, just go back to Plato in Euthyphro. I mean, Socrates already stated the problem. He said, look, let's even agree that the pious is what the gods love, right? A pious act is an act that's pleasing to the gods. Mm-hmm. Take that even as a necessary and sufficient condition. That still leaves the question, is it pious because the gods love it, or do the gods love it because it's pious? And Socrates gives, it seems to me, a perfectly good argument that it's the second one, that it's because it's pious. If there are gods and they're pleased that you do something, let's say morally good, they're pleased because it's morally good. They're being pleased isn't what makes it morally good. It's being morally good that makes them pleased. And therefore, even if they didn't exist, it would still be morally good, right? God, whether or not there's a God, even God wouldn't have the power to make something morally good.
But yeah, I mean, I think that's getting at the crux of the issue, right? Like, there is a normative standard. There's a normative ethical standard, and there are only two options. Either it is something that comes from us, given the kind of creature that we are, given our physiology, given our cognition, given our structure, or it doesn't. And both of those instances people find uncomfortable for different reasons, right? Like, people don't like thinking that it's just physiological. Then you're led into the whole, well, aren't we just machines? Aren't we just automata? But people also are skeptical of the idea that it doesn't come from our physiology, because then where does it come from?
Right. And I mean, again, and this is, I spent a lot of time with Plato, and I think he was right on target. You can ask the same question about mathematics.
Yes, exactly.
Right? And that's why he uses the mathematical proof in Meno. Yeah, but no, the facts of Euclidean geometry are facts of Euclidean geometry. They don't come from us. We discover them insofar as we can by proofs, right? We discover them by thinking, but they're there independently of us. Where do they come from? They don't, I don't know. They didn't, again, God didn't make it. God didn't make it true that the square on the diagonal is twice the area of the square. That God doesn't have the power to change that either. These are just mathematical truths. Their foundation is in mathematical reality. I think they're moral truths. Their foundation is in moral reality. And whether there's any theological reality, personally, I don't believe it because I don't see any evidence of it. But even if there were, I don't think that it would impact moral reality to any more extent than it would impact mathematical reality. It would just be, okay, there's a realm of, some theological beings. I don't see any evidence of it. I have no reason to believe there are such things.
Yeah, and I mean, also even a way simpler point that physics changes all the time. Like, what physics will be in 100 years from now, what the interpretations of quantum mechanics will be in 100 years from now will be just not recognizable as to what we have today. And that's a long and painful process to get there. I don't think it's a great idea to make big claims about meaning and your place in the universe based on what our inevitably preliminary versions of the theory.
Well, that's on the one hand, that's true. On the other hand, I just don't see that they have any real relevance.
Yeah, I mean, why entertain it at all?
Gee, if it turns out string theory is correct, what does that have to do with whether I should go comfort my daughter when she's, falls down and skins her knee on the playground? Nothing, zero.
Yeah.
Right. New discoveries in foundations of physics will be quite interesting, but they're not going to have moral consequences. How could they?
Yeah, no, for sure. And that's not to say that there isn't work to be done in thinking about moral consequence. It's not in fundamental physics.
Yeah. Yeah. So if people, you can perfectly well ask, and in a certain sense, it's the deep question, what is the best life for a human being, right? And that, again, Socrates, right? Anexeristos bios ubiotos anthropou, right? The unexamined life is not worth living for a human being. That's one part of an answer, right? That part of what makes a really admirable human life is asking certain questions and posing them to yourself. Now, you can also question that, and you can say, look, Socrates, maybe I'm somebody who just doesn't ask those questions, but I spend my day in, saving people in an emergency room in a hospital, and you're going to tell me that that's not worth doing because I don't sit around doing philosophy. All right, so Socrates also is not, you can question him as well, but that question about the significance of how you spend your time, such as you have it, just strikes me as something that isn't much impacted, as far as I can tell, as somebody who spent most of his life worrying about physics. It's just physics doesn't feed into it, right? It's a different kind of question.
Yeah, and I think not just with physicists, but with scientists in general, there's a tendency in popular domains to associate scientific authority with all intellectual authority, right? Like if you have some piece of knowledge on physics, you should have some claim towards true claims about everything.
Yeah, well, that's a bad idea. I mean, look, if you take the Big Bang Theory seriously, and there's a grain of truth in it, physicists have a wildly out of scale self-image as to how intelligent they are in general, right? And the deepest discipline there is, which is also complete nonsense, right? I mean, neurophysiology and cell biology and embryology are really hard, and we don't understand them well, and really smart people work on them. They don't really have to know anything, much of anything about physics. Why should they have to? But also this idea that somehow they're just so clever that they can see. No, I mean, take any question, and for that question, you have to ask, what are the possible answers, and what are the reasons for believing the answers, and so on. And one thing we know is that physicists also tend to often be quite naive about the nature of physics. I mean, the nature of physics is a discipline. They may understand the physics of physical objects, but have a very naive philosophy of science, or a very naive understanding of how science works. But why not? I mean, it's not their discipline. They didn't learn, they weren't taking courses in philosophy of science. They were taking courses in physics. It's just that they seem to have the idea that either they're innately so smart that everything else is just trivial, or somehow they've gotten it by osmosis without studying it. But no, sorry.
Yeah. What just shifting gears a little bit, what are your hopes and dreams for the future of foundational physics?
Well, my hope is very explicit. It's that it become recognized as an actual discipline. And I'm trying to do that. I mean, I'm practically trying to do that. That's why I founded this John Bell Institute for the Foundations of Physics, and why by charter we have 6 people on the board of governors, and 2 are philosophers, 2 are physicists, and 2 are mathematicians, because it's a field that requires abilities in all of those fields. And it's a field that's not recognized, just institutionally unrecognized in the university. As I like to say, that the easiest place to do foundations of physics is in a philosophy department, which is kind of loopy, right? And it's easier to get a job doing it in a math department as a mathematical physicist, and that has to do with this funny way that mathematical physics ended up in math departments rather than physics departments.
Right.
And the most hostile environment to do foundations of physics among those three is in a physics department, which is kind of crazy because you think it's actually foundations of physics.
Right.
So, you know, it's this, I think, clearly defined discipline that doesn't fit into the modern university structure. And so it's been fragmented because there aren't that many people to do it. It's fragmented across the world. And it needs a home and it needs recognition. And I can't give it recognition, but I can try and give it a home. That's what I'm trying to do, is actually have a physical place
Right.
where people will come to do foundations of physics and get it some, you know, try and get it recognized as what it is, because it's not well understood. Certainly, you know, I say a lot of people do this in philosophy departments, but in a lot of philosophy departments, also people in the philosophy department saying, why the hell are you here? Right? Why are we hosting you? Why aren't you over in the physics department or something? And
Yeah, I mean,
you know,
most philosophers.
it wears on you after a while. You know?
No, but I mean, like you just have to express gratitude towards yourself and what you're doing. Like really, you are at the forefront of creating foundational physics as a discipline between those three. Like I can't understand physics without having read math, physics, and philosophy. I don't know how anyone does.
And I, you know, as I've said, look, if you look at the 20th century and you ask me who are the best philosophers of physics,
Yes.
I'd say in the early part it was Einstein, and in the later part it was Bell. Okay, and both of them were officially physicists, but they were extremely intelligent and interested and clear thinkers doing, you know, the paradigm work in what I would, you know, what you ought to call philosophy of physics, if there is such a thing, but it's foundational works. It's, you know, doing physics with a certain sensitivity to foundational questions.
Right. Have you, because I know you've read a lot of history. You mentioned you did have part of your degree in history. Have you found that?
I think it's very important. I mean, I think it's tragic how little real history physicists understand. And we've already talked about that. I mean, when you think Schrodinger was trying to convince you there are cats that are neither dead or alive, I mean, you're so far off track. How many physicists have ever gone back and read that paper, which is also just a very nice paper, and understand that it was Schrodinger's response to the EPR paper? I mean, the history of physics is fascinating. And physicists, you know, it's wonderful reading Maxwell. It's wonderful reading Boltzmann. They were very aware of what they were doing and very aware of the conceptual issues and discussed them. I mean, you know, you should do history of physics not out of antiquarian interest, but just to remind yourself of what physics was until this shut up and calculate stuff ruined it.
Yeah, I mean, I find that a lot in computer science with Turing. Like Turing's 1951 paper, where that kind of starts the enterprise of looking for intelligent machines, explicitly says that that question is not a coherent one. That to try to equate the kind of conscious experience that people have and the kind of intelligence that machines might exhibit using computational techniques that have been developed are an equivalency that doesn't make sense. It's begging a philosophical question that isn't fleshed out yet. And so much of contemporary computer science and the people who think about these questions are not informed about that. And I mean, that's not even mentioning AI as a field.
Yeah. I mean, I just had a debate on Facebook about somebody has a machine and they ask this question of the machine. It was this kind of very coy question, right? You're in the most famous French museum looking at the most famous painting and thinking of an animated character who has the same name as the person who painted this painting, and what is that, and that character is holding something in their hand. What country does it come from? All right, so it was like this, and they give it to this machine, and this machine says it comes from Japan. All right, and they're going, wow. And, are you telling me machines can't think? But in the course of this, it says it identifies the Louvre and the Mona Lisa and Leonardo da Vinci, and then it says, and Leonardo da Vinci held a katana in his hands. And you say, Leonardo da Vinci never held a goddamn katana in his hands, right? This is not only not evidence that it thinks, it's clear evidence it's not thinking, right?
Yes.
It's not actually formulating thoughts.
Yes.
It's okay, they did a good algorithm that's searching, that can search and spit out answers like this and get to Japan. Yes, but it's obviously not thinking. And really there were people again who were just saying, oh, but like if you pass the Turing test, doesn't that mean you can think? And you want to say, no.
That's not what Turing meant.
And then they say, but what evidence do you have that I can think, if not just this verbal behavior? And I said, well, you're a human being, you've got a brain. I know you had a childhood. I know you learned more or less the way humans learn. Yes. All of that is really relevant evidence.
Yes.
That what's going on in your head is really similar to what's going on in my head.
Yes.
And we know that's not what's going on in the computer, right? It's not even a guess. We know it's doing something extremely different.
Yes.
And the word thought was introduced to talk about the stuff going on in human heads.
Yes.
Right. And that kind of naivete in which people think, oh, but Turing taught us that all you have to do is, look at the behavior. You want to say, behaviorism, again, and behaviorism was a kind of very naive implementation of this empiricist semantics, which also has been completely refuted every way you could possibly refute it.
Quite famously.
Kind of naively carry this along.
No, you're right. I think there are these just skeletons that, as many times as they're refuted, they keep coming back up. Like Humean empiricism, behaviorism, the kind of like the strong Kuhnian type of arguments. They just keep coming up no matter how many times you point out the disclarity between them. Like what you were talking about. The reason that the machine and the mind are different is because we know what's going on in the machine because we programmed it that way. We don't know what's going on in the mind because we don't have a good enough theory of it. So you're begging the question. We need a good enough theory to be able to pose a comparison between them.
There's that, and there's also just evidence. I mean, at one point has this nice example where they made these computers that could play a really good game of chess by doing this massive search.
Yeah.
But you can set up very artificial looking chess problems that even a duffer like me is not going to make the mistake the computer makes, because they're kind of set up so that the problem is beyond its search horizon, right?
Yep.
And so the computer makes errors that even a mediocre human player wouldn't make. Yeah. And you sort of furthermore understand why it made the error, because it's beyond its search horizon. But humans don't do it that way, right? We're just not thinking about the problem the same way.
Yes.
Now that's not to say you couldn't, in principle, make a computer that does what a human does.
Right.
It is to say that we know for certain computers they're not doing what humans do, no matter how convincing their external behavior might be.
Right. Some element of human cognition has to be different from just algorithmic certainty.